Before we move on to solving actual mechanics problems using Lagrangian mechanics, we have to deal with one additional issue, that of constrained systems. The Lagrange mechanics we have done so far specifies that for a system of n particles, we will get 3n Lagrange equations, and they will all have to be solved in principle for us to understand the motion of the system. This works in principle, at least as long as all the forces are conservative, and at least on a microscopic scale that is true. The problem is that it is often unnecessarily complex when we're dealing with a real system, and we would like a way to simplify the calculations, taking into account constraints, and here we're going to see how to do this. So as an example, let's consider a pendulum. It consists of a beam here that's massless and length L. It's attached to a bob of mass m. This bob moves in a plane where we have two coordinates x and y, so that means that we have two spatial coordinates associated with this bob, so we should have two Lagrange equations. And we should be able to write those down as long as we can figure out what the potential is that corresponds to all the forces on the bob. Now there are two forces that act on this bob. We have, of course, mg going down, and then we have the force of tension, which pulls in the direction of the beam. Mg, well, the force of gravity, we know there's a potential associated with this. So if you're going to write down the potential mg here, we get mgh. This is your gravity. And then we have to find a potential associated with the tension. Now, at first blush, that seems difficult because it's hard to see. This tension here is set so that the beam is of constant length. But if you think about it physically, there's no such thing as an infinitely stiff beam. The beam can actually stretch, and does stretch if a sufficiently large force is put on it. So it can be seen as a spring. So we do get this tension force as a result of a slight stretching of this beam. So we can add in a potential associated with the beam, as well, as we'll see in a minute. Now, we'd like to write this mgh here in terms of things that we know. So I guess it will be minus mgy. And then we have the beam's potential, its spring potential. So we get 1/2 k. And I'll take that to be r minus L squared. So that if r changes from L, we get some potential energy. Now k here is very large. And that's the important part. And this is the way we're going to do it. In principle, if we want to take into account all the forces, then we'll also need the kinetic energy. That's relatively easy. That's going to be 1/2 mx dot squared plus 1/2 my dot squared. Okay, and then we can solve this and find out something about the motion of this pendulum. The problem is that it's unnecessarily complex to do so. The first thing we'll note is that y here actually is going to be equal to r times 1 minus cosine of phi. And also we can rewrite this kinetic energy here in terms of polar coordinates, if we like, as 1/2 mr dot squared plus 1/2 mr phi dot squared. So what this does, this term here, is it will couple the motion in phi and the motion in r in some complicated way. In other words, the bob will swing side to side while the length also varies. This is actually a pretty complicated problem to solve, and not something that we'd like to attack. It also doesn't give us any real physical insight because, for all intents and purposes, this beam stays at a constant length. So it will be much easier if we could just assume that this beam is of a constant length. After all, k is very large, and that means that any energy that we would need to really change the length of this beam in a way that matters will be much larger than the energy associated with the swinging of the pendulum back and forth. So we can actually take L to be a constant. So to do that, to avoid this complexity, we will introduce a constraint. We have seen this earlier, actually, when we talked about one-dimensional motion along a curved path, for instance, as is undergone by a train. Then we talked about constraint forces, and we saw that we could actually ignore those constraint forces under the right circumstances, and that's what's going to happen here as well. So let's introduce the constraint. The constraint will just be that x squared plus y squared equals L, taking the origin to be here, the point where the pendulum is attached to the ceiling. Or in polar coordinates, we can just write that R equals L. Okay? So this leads to a change in our kinetic and potential energies. So we had U, and we're going to work now in polar coordinates because that's really simpler. We said that U is equal to mgh, which is really mgr times 1 minus cosine phi plus 1/2 kr minus L squared. That was what we had for the potential in polar coordinates. And we will stick to polar coordinates. Polar coordinates. Because things are simpler there. Okay, R equals L. Well, that means that the potential energy here is actually equal to mgl times 1 minus cosine phi, and then this becomes 0. That's simpler. And for the kinetic energy, well, R doesn't change. Let me write this down. 1m r dot squared plus 1/2 m r squared phi dot squared. R doesn't change, so R dot is 0. So this term must be 0. And then this is constant, so the kinetic energy is now just equal to 1/2 ml squared phi dot squared. Okay, so this gives us that the Lagrangian, now only depending on one variable, phi dot and t, well, depends only on one spatial variable and the corresponding velocity, of course. It's t minus u, so that's equal to, therefore, 1/2 ml squared phi dot squared minus mgl 1 minus cosine phi. So this is now a Lagrangian in one equation, in one variable. So this should lead us to one Lagrange equation. Specifically, the L d phi minus d dt acting on the L d phi dot equals 0. And then we can just plug in the Lagrangian, and we will get, as we'll see, minus mgl times sine theta. It's the derivative of cosine there. With 3 minus signs, we have minus, minus, and then another minus from the derivative. And then we have to subtract. And this is now simple because L is a constant. And the way we had formulated before, L would have been equal to R, and this would have been more complicated. But we end up with this equation. Turns out this is the torque, and this is the angular momentum. So really this is actually equivalent to the torque equals the time derivative of the angular momentum. This is Newton's second law. We're not going to solve this now, but we can see that this is just one equation, like we said, and it's going to be And it's much simpler than it would have been if we hadn't applied this constraint. So what happened here was that we had two Cartesian coordinates, x and y. We applied one constraint. This is the constraint here. Let me put that in a box. We applied one constraint, and then that reduced us to a situation where we had 1 degree of freedom. So we started with two coordinates plus one constraint. And since 2 minus 1 is 1, this gives us 1 degree of freedom, which is represented by the variable phi here, right? Of course, we didn't have to use phi. We could have used x just as well. We could have used this version of the constraint, so we're not forced to use phi. It just happens to be the simplest choice. And you should always make the simplest choice, obviously. So let me then extend that to another case here. So let's just write down what we had here for the pendulum. We were looking at the pendulum. Two Cartesian coordinates, one constraint, and therefore 1 degree of freedom. Another example we can think about will be the double pendulum. We'll talk more about the double pendulum later, but here it's just for illustration. It has two particles that can move, and there are two coordinates associated with each of them, so we actually have here 4 Cartesian coordinates. We have two constraints. This pendulum is of constant length L1, and this one is of constant length L2. And that means that we have 2 degrees of freedom. Okay, so generally speaking, we can take the number of degrees of freedom equals the number of Cartesian coordinates minus the number of constraints. Okay. Now, degree of freedom is something I need to define more specifically. So here is my definition of degree of freedom. So the number of degrees of freedom of your system is the number of independent directions, and then I count both back and forth as independent directions. A system can be displaced into by using small motions. Okay. So, for instance, for our double pendulum here, if we're looking at this configuration and we're just looking at small changes from this equilibrium, well, we can move this pendulum back and forth a little bit, and we can move this pendulum back and forth. So we have 2 degrees of freedom. So if the number of degrees of freedom in an n-particle system is less than 3n, then we say that the system is constrained. Okay. Now, just because you have a constraint, and that reduces the number of degrees of freedom from 3n to something less, that does not mean necessarily that the Lagrangian approach will work. There's one other thing that we need, and that's what's known as a holonomic system. So that means I have to define that as well. Right. So if the number of degrees of freedom equals the minimum number of generalized coordinates, then the system is holonomic. And it turns out we can only actually deal with holonomic systems. So if we look, for instance, at the double pendulum here, we have determined that we have 2 degrees of freedom just by looking at how these particles can move. But we can describe the system completely also with only 2 variables here, phi1 and phi2. So this is a holonomic system. Okay. So that's fine. We will be able to solve this particular problem with a double pendulum. Now let's consider a different case here. This is supposed to be a ball rolling on a flat surface. Now, this system is not holonomic. The double pendulum is holonomic. The ball on the plane is not holonomic. Okay, we will talk more about that in class. But until then, I'd like you to think about why that might be. Why is the system of a ball rolling on a flat surface not holonomic? Now, we're not going to deal with holonomic systems here. Basically, all the systems that we will approach that are covered by Hamilton's principle have to be holonomic. And all the forces have to be conservative. Or at the very least, we have to be able to write all the forces as the gradient of some potential, but that potential could depend on time, which means that actually the forces aren't truly conservative. But we have to have the second condition for conservative forces be valid. Oh, and there's a minus sign in front here. Let's put the minus sign there. Now there is actually, I should mention in passing, ways to get around this. I mentioned it before. There's something called D'Alembert's principle. In that case, you can deal with forces that are not on this form, and you can also approach at least some cases of non-holonomic constraints. Not every case, but some cases. So it's not quite as limiting as it seems. But even with these limitations, we can still attack a great many of the problems that we encounter in physics, because non-holonomic constraints, especially on a microscopic level, are actually not that common. So the way we're going to proceed here is that we're going to use generalized coordinates. Which is now a function of the position of all the particles. But the number of generalized coordinates might be less than 3n. We are going to require the number of generalized coordinates to be the smallest it can be, okay, in order to describe the motion of the system. So we will do that by applying mathematical constraints. Every constraint will correspond to a formula such as this one, and then we'll reduce the number of variables that we're working with, or at least it will, provided that our system is holonomic. And then we will work from there. So this is the background of constrained systems. In the next video, we're going to actually prove that Lagrange's equations are valid in a system where we have constraints and the number of generalized coordinates is smaller than the number of Cartesian coordinates.